So I don't know how much y'all remember about powers and roots, but we're going to be going back into this now because this is where we really start getting into what you need to be able to use to get further in this field. Okay, so if everybody remembers what exponential form is, right? You have your base and your exponent. What does that exponent mean? How many times that number is going to be multiplied by itself? Yes. Very good. So if we do 3 to the 4th, that's 81. 4 to the 3rd, that's 64. 2 to the 5th, that's 32. And 5 to the 2nd, which is 25. Now, I'm going to go ahead and point this out just because this is one of those things that I always try and point out when I'm doing these. What's a really fast way I could solve this without entering it into a calculator? Yes, so if you take them and start grouping them, like 3 times 3 and 3 times 3, that's 9 times 9. 9 times 9 is 81. Or if I need to start working with this guy, I'd say, well, 2 times 2, 2 times 2, that's 4, that's 4, that's 2. So 4 times 4 is what? It's 16, and then times 2 would equal 32. So it's just a little bit of an easy way to kind of knock that kind of a problem out with a little bit less grabbing of the calculator. Does it make sense to everybody?
Yes, ma'am.
Okay. So this is 3 squared, which is 9. A lot of different ways you can say it. 3 squared, 3 to the 2nd, so on and so forth. And then you have what's called the cube, which is 4 to the third, the number to the 3rd power. Everybody following along all right? So then we have squares. This is a number raised to the 2nd power, or the base number multiplied times itself. We kind of like those, right? Because it makes them, they're really typically fairly easy. Now then, quick question. Who has their scientific calculator with trig functions? Just kind of a raise your hands kind of thing. Just 2 people?
You're asking about if I have calculator with the scientific calculation?
Yes.
I have one. Yes, ma'am.
Okay. Those of you that don't have them, you need to go ahead and make sure you get them. But if you take your calculator out and you're trying to look for that square key, or if you're trying to just put it to some other kind of power, because we will be doing that a lot, then you need to look for one of 2 buttons. If you're trying to just square it, you usually have an x to the 2. Or if you're trying to do something like, say you've got 2 times, like you have 2 to the 10th. Well, I don't know about you, I don't really want to mess with having to do it the long way, so I'd probably end up doing it a different way. So the way I would end up doing it on my calculator, and this is going to vary for each calculator. Like I said, my preference has been for a while now the TI-30X 2S, and that's just because that's one that I've used for several years. I'm very used to it. But the good thing is that it has a button on it. On the left-hand side of the button keypad, it has one that's a little arrow that points up. So it's this long, skinny little button, and it just has an arrow pointing up. That particular key, if I type into my calculator 13, and I put that little raise to the 5th, I should end up with 371,293. Because what this does is just tell it I'm raising it to a power. I don't know about other calculators. In other calculators, you might have to sit there and enter 13 times itself 5 times. But I'll leave that to y'all to figure out. Normally, a lot of these calculators come with what I like to call the cheat sheet. I don't know how many of you have ever seen the cheat sheet. But it will walk you through how to do your powers and roots, and it talks to you about how to do statistics and memory and all that. So make sure you don't throw that particular card away. It does really give you some good information. Okay, so 4-6. The symbol is the radical sign, which is used to tell you to find the root or base of the number. The small number inside the radical shows the number of times that the base was multiplied together to get 9. So what times itself twice gives you 9? It is 3.
3.
It is 3. It's 3. So again, you have a couple different buttons to help you with this on your calculator. You have one that's the square root key, but are we probably going to be sticking strictly to the square root key, you think? Okay, so yes, you will be using the square root key, but you will also be using the root key. Now the root key, what's going to do is that if I happen to type into my calculator, let's say I'm looking for the quarter root of 81. So what I would have in my calculator would be 4 the square root, the quarter root of 81, which is equal to 3, by the way. So what it did was it broke it down and tried to find that main root. Okay? That makes sense? Okay? So, powers of powers. Anybody remember how to do any of this so far? Sort of. Okay. So looking at the powers of the powers.
Uh,
Go
the
ahead.
power times the power,
Mm-hmm.
and then times the number we have.
Yes. So in this case, we start off with 5 to the third squared. So you can do this a couple of different ways. The easiest is to multiply your exponents together so that you end up with 5 to the sixth, and that will end up being your 15,625. Um, yeah. Fractional exponents. Now, fractional exponents are kind of neat. I will not lie. They are probably one of the neater things to talk about. And I'm going to tell you why. So right now they've got 27 and they want the 1/3 exponent. So what that actually means is that they're wanting the cube root of 27, which is what? What times itself 3 times gives you 27? I got somebody says 3. Does everybody agree?
Yes, ma'am.
That would be correct. Because 3 times 3 is 9, 9 times 3 is 27. Now, instead of the 1/3 root, what if I said I wanted to find the 2/3 root? I'm sorry, the 2/3 of this. Then what you would do is you would find your cube root, which is equal to 3, and then you would have to square it to use that numerator. So your answer overall would be 9. That is the 2/3 of what you got. Does it make sense to everybody? Like I said, I don't really torture y'all much with that one because it's just not one of those things you're going to use a lot of. But that way you do know how to solve it if you need to. Okay. So powers of 10 are useful for very large or very small numbers. Using exponents, we can reduce the size of the number. So I can take 1,000 down to 1 times 10 to the third. Now, before I go any further, how many of you know anything about metric system? Anybody at all? So some of y'all might remember that King Henry danced merrily drinking chocolate milk. Y'all remember that old rhyme? Kinda, sorta. That was supposed to stand for most of the, so it would be kilo, hecto, deca, 0, milli, no, not milli, deci, centi, milli. Well, this is kind of where we're going with this. That's kind of what we're going to be getting into. Okay. So so let me kind of explain this a different way than what they do here because I'm not a big fan of how they explain it. So let me go to a different color here so it shows up a bit better. So what they've started off with is saying that we have the number 400. Now, in order to get the number 400, you have to understand one thing about working with these numbers, and that's the fact that your decimal place will be moving. But when you're moving that decimal place, you're not wanting to change the value of the number, you're just wanting to put it in shorthand. If that makes any sense? Does everybody even know what shorthand is? Anybody at all? What it means is that my decimal point that sits out here, that gives what part of what gives a number meaning. Technically, the way a number actually works, and you could kind of see this with old computers, is that you end up with a bunch of zeros in the very front of a number, and then after that decimal, you start seeing more zeros. Okay? So what we're allowing our decimal point to do is to step out of its stringent role, but we're doing it in a way that works for what the equipment is supposed to do. So in order to get something like 4 times 2 to the 10 to the second, what I would do is move my decimal point 1, 2. When I moved it, I put the number of times I moved that exponent, moved the decimal as part of my exponent. Does that make sense so far?
Yes, ma'am.
Now, what they're showing you now is the fact that once I've got my decimal point right here, and I need to know what that number actually is in real life, I have to move it back out to its original position. So I'm going to take my exponent, and I'm going to take my decimal place that's always understood to be at the end of a number, right? And I'm going to move it back to its original place by going back 2 spaces in this case. Does that make sense to everybody? Yes, no, kind of, sort of, maybe?
Yes, ma'am.
So when I'm trying to make my whole number, and that's a number that's in front of this decimal, into one of these, to convert it to a power of 10, I've moved it forward. To convert it from that power of 10 back to a decimal, I move it back. Okay. So chart for the powers of 10, you have 10 to the 0, which would cancel out, meaning that you have the decimal of 1. Okay. 10 to the 1 is 10, obviously. Squared is 100. So what you should notice is that every time I have my exponent, it's matching the number of zeros behind my comma, right? Everybody see that? So converting the negative powers of 10, By using exponents, we can reduce the size of the number. So instead of, and guys, I'll go ahead and tell you this, when you're dealing with numbers like these and you're having to do conversions and such, having a comma or finding a way to visually break between sets of zeros or whatever number you're dealing with is a very good idea and a good way to track where you're having to move things. So when we get behind the decimal, we generally don't care, but whenever you're dealing with powers and roots and you have to be able to track how to move that decimal, you want to kind of go in and do like we do with whole numbers. What do we do with whole numbers is we add what? So we've got a denomination. You use a comma, right? So whenever I write the number 1000, I always put a comma after the 1, right? Well, in this case, you're doing the same thing, only you're working behind that decimal. So you just go in and go, here's a comma here, and that visually breaks that number from, oh, look at all the zeros, to, oh, there's 1, 2, 3, 4, 5 zeros with a 5 at the end. Does it make sense to everybody?
Yes, ma'am.
Everybody else look good? So the way they got 10 to the 6 is they took the decimal point, and whenever I move it forward, that means I am getting positive exponents. However, when I move it this way, my exponents become negative. Okay? So if I move it 1, 2, 3, 4, 5, 6. That is how we get 10 to the negative 6. Okay? Questions? Okay. So when converting negative, so if we're dealing with negative numbers, so anytime you see this little minus sign, you are dealing behind the decimal. Does that make sense to everybody? Okay. So in dealing behind the decimal, that means that if I have 4.7 times 10 to the negative 3, that means that I had my decimal point out here, and I had to move it 1, 2, 3 places to get my negative 3. So in order to write it back out the other way to get my decimal point in its original position, I take my decimal point and I go, well, that's 1, 2, 3. Fill that in with the zeros that are hanging out there, and then you're back to your original decimal format. Does that make sense?
Yes, ma'am.
Okay. So working with negative powers of 10, again, 10 to the 0 is 1, 10 to the negative 1 is 0.1, 2 is 0.01, so on and so forth. Now what you should notice is that anytime you have your negative, like you have a negative 1, you have your 1 that's gone only one place behind that decimal. Negative 2, it's moved 2 places. 3, moved 3 places, so on and so forth. All right. So to use your calculator with powers of 10, you have to find your exponent key. On some of them, they're an EXP. On some of them, they're an EE, and you have an EEX. Now, guys, I will go ahead and tell you, be very, very careful about how you enter a lot of this, because sometimes the EE or EX is already multiplied whatever you've done by a power of 10 to the 1. So thus when you add some more to it, then it starts really throwing your numbers off. For certain calculators, you can enter the equation a little bit differently without having to use these. My way to enter it into my calculator, and again, that's the one I've got, which is the Texas Instruments 30X2S. So the way I generally will enter it is, let's say I've got 12 times 10 to the 4th. In my calculator, I would put it as 12 times 10, use the little up arrow, and 4. Because it's the exact same thing. Does that make sense? So you might have to take your calculator and play around with it for a little bit. So it might take a little bit more finesse to work with it. But that's kind of what you have to do to start working with your calculator to find out what kind of quirks it has as far as that goes. All right, so when adding or subtracting powers of 10, the exponents must be the same. Okay, the exponents must be the same. Now, I'll go ahead and tell you my rule of thumb with powers of 10, guys. And this is one I adhere to strictly. And that is, when in doubt, write it out. When in doubt, write it out. What do y'all think I mean by that? It's easier to understand if you write it down. That is certainly a good point. The biggest one I can tell you is, until you become comfortable with this decimal being on the move, the easiest way you can deal with this when you've got a decimal on the move like this is to write it out until you're used to moving that decimal. Does that make sense? Because to us, all we've ever been taught, especially in mathematics, is that that decimal point is a fixed place. It doesn't move. So now you have to get over the concept of it doesn't move and take on the concept of it can be moved as long as I track its use and its movement. Does that make sense? So when in doubt, write it out. So looking at numbers like these, so I have 2 times 10 to the second and 3 times 10 to the third. In reality, these numbers are 200 and 3,000. So I have 203,000. That can kind of change your perception of the number. So there's a couple of different ways that I could redo this whole problem. So yes, I can solve it by making 3 to the 10, 3 times 10 to the third into 3 times 30 times 10 to the second. That would work. Another way I could solve this is moving my decimal point from behind this 2 to just in front of it. So I would end up with a problem of 3 times 10 to the third plus 0.2 times 10 to the third. Because either way, I would end up with 3.2 times 10 to the third. Does everybody see how I did that? So like I said, when in doubt, write it out until you get completely 100% comfortable with the idea and the process of moving that decimal. Write the number out into the long form of it, just so that you have an easier time visually seeing how you move that decimal. Okay? Subtracting powers of 10, same thing. You have to convert it to where your exponents are the same. So my first number is 3 times 10 to the 6th minus 2 times 10 to the 4th. So there's one or two ways that I can deal with this 10 to the 6th and this 10 to the 4th. The way they show you is they take 10 to the 6th and turn it to 310 to the 4th. And again, there's nothing wrong with that. The other way you can do it, though, is you leave this as 3 times 10 to the 6th. And you subtract, my decimal point's right here, so I can move it 1, 2 places forward. So you ended up with 0.02 times 10 to the 6th. 3 minus 0.02, you would end up with, so you end up bring up down your 10 to the 6th. 3 to minus 0.02 would be 2.98. Does everybody see how I did that? Does anybody have any questions over what I just did and how and why I did it the way I did? Any questions at all, guys? Now it's time to ask them.
No, ma'am. Thank you.
Nobody has any questions whatsoever. Okay. So I'm going to give y'all a couple of minutes to work on these problems, and then we'll go over them and see how well y'all did. So I'll give y'all just a few minutes to work on those. And then after this, we'll take about a 10-15 minute break. Sound good?
Yes, ma'am.
All right, guys, so I've got the answers up. How well y'all do?
So we have to do the answer like this, or
Yes.
do we have to do the final answer?
These are the final answers. So
Okay.
you can work them out in long form. That's not kind of the problem with this. Is what I was trying to kind of encourage y'all to do. Is yes, you writing them out is a good way to go ahead and learn how to move between these. Um, it's one of the better ways I know of to kind of teach this is to help y'all learn how to really interpret these. Because that typically, this is where a lot of people end up tripping up and stuff like this is because um, we start getting into these kind of details and a lot of people don't know anything about metric or having to deal with exponents. So with the first one, it was just pretty much an add straight across because your exponents were exactly the same. But like I said, if you were writing them out, that is a good way to go ahead and get used to this. So you should have gotten 6,000 plus 2,000, which would equal 8,000, or when you put it back in short form, get you get 8 times 10 to the third. Same for the subtraction problem. For the third one, this is where you might want
Yeah,
to.
I need you to explain to me the third one. Yes.
Okay, so the third one is a little bit more fun and interesting here. Because what you needed to do is one of two things. Either you could make this into 20 times 10 to the fourth, I'm sorry, times 10 to the third, or you could make this into 0.6 times 10 to the fourth. And how do I know that? Well, let me change ink colors real quick here. I know that 6 times 10 to the third is 6,000. That's the long form of it. 2 to the fourth is 20,000. And how do I know that? Well, this guy right here tells me that I moved that decimal 4 places. So that's in order to bring it back out, I once again have to move my decimal another 4 places, but in the other direction. That's what gave me that one. So when you add 20,000 to 6,000, you would get 26,000, and then once you get so then again, your decimal is understood to be back here, even though we don't generally write our decimal at the end of the number, because what's the point unless we're doing a decimal? In this case, you need to know that it is understood to be there. So whenever I need to put this back in a short form, I move it 1, 2, 3, 4, and that's how you get 2.610 to the fourth. So no matter which way you kind of solve this one, yeah, you'll see what I did though. Any questions on it?
Well, this is the way how you get 2.6. You have to make it big and then move the decimal for like 4 times, right?
You can make it into the bigger numbers, yes. You can also do what I did over here where I just took the decimal that's behind the 6 and moved it in front of it, which allowed me to make this into 0.610 to the fourth. The other way you could do this, and this is the one that they try and teach you in the textbook, but I don't really care which way you use as long as you know what you're doing when you use it. This is why I go back to that So you really get into comfortable with moving that decimal, just write the number out so you can visually see and compare what you're doing versus what is needing to be done. Excuse me. So then I think the next one y'all probably might have had questions about was the last one right here. Am I right?
Yes, ma'am.
All right, so again, this one is kind of an interesting one. There's a couple of different ways you could have done it. To begin with, you have to understand that this is 4 times 10 to the negative 2. So I have my 4. In order to get to that 4, I had to move my decimal place 1, 2. So I start off with 0.04. With this guy, I moved it I have my 5 and move that decimal 3 places. So I move it back out those 3 places and you get 0.005. So there's a couple of different ways you can deal with this. You can take your decimal behind your 4 and move it back 1 place. So you end up with 4 times 10 to the negative 3. Or you can take your decimal from behind your 5, move it back once, and get 5 times 10 to the negative 2. Does everybody see what I did?
Yeah, I see, but it was confusing for me. The last one I understand it's 5 times 10 to negative 2, but the other one, why we don't need to go like backward because we went like -1
Well, the whole thing is that
up
I'm
front.
showing you a
This is
couple of different ways you could change your numbers around here. So that's why I say write it out, is because let's say I decide I want to look at the equation as 0.040 plus 0.005. I can look at it that way, because that would be the 4 times 10 to the negative 3. I'm sorry, not 4, it'd be 40. And then adding that to 5 times 10 to the negative 3. So all I did was I took my decimal from my base number and moved it 3 places. This one was already moved 3 places because that was our original number set. The other way I can solve this is I only move it from, I'm going to erase some ink here.
Oh, I see it now.
So then the other way I could do it is, so I once again have my 0.04 plus my 0.005. So when I move my decimal place this time, I want to move it only 2 places. So I end up with 4 times 10 to the negative 2. And then I add, so if I move it 2 places here, I'll move it 2 places here. So that's how I get 0.5 10 to the negative 2. Does that make a little more sense to everybody?
Yes, ma'am.
This is why I said write it out and get used to manipulating these numbers. simply because this is what you'll be doing a lot with this. And we'll discuss why here in just a minute. But in the meantime, has anybody got any more questions about any of these questions?
No, man.
Anybody at all? All right, so before we get into multiplying, let's talk about multiplying powers of 10. So the way you do this, guys, is you're going to, if you remember when we did fractions, what did we do? What did we do with fractions to add and subtract them? You did have to put them in like denominators, but the biggest thing you did was you took the whole numbers away from the partial numbers. Do y'all remember that? So you're going to do the same thing here. You're going to take your numbers like 100, and you're going to multiply it by 2. Then you're going to take your exponents, so you have 10 to the 5th, you have 10 to the 3rd. So what you're going to do is you're going to leave your whole numbers, these first numbers, like this one and this one, you're going to do just whatever this guy says, which is multiply, in this case. So what you do after that is dealing with your exponents. And in this case, anytime you see multiply when you're dealing with exponents, you're going to add the exponents. You're going to add the tops. And yes, it should be 200 times 10 to the 8th. Let me erase all the ink on the slide and we'll kind of look at that. So you do end up with 100 times 2, which is 200. 5 plus 3 is 8. So your overall answer should be 200 times 10 to the 8th. Or you can simplify it down to 2 times 10 to the 10th. There's a bunch of different ways we can solve these, which we'll go over as we go through all this. That make it a little bit easier and less having to deal with other things. And then dividing powers of 10, you do the same thing, but we'll get into that here in a minute. Excuse me. So let's talk about special forms of powers of 10. So if you go back in your memory to your science class or to your mathematics classes and such whenever you were in grade school, you should have some minor recollection of all this, right? It's been sitting at the very back of your head, the bit of useless knowledge that's just about gone to the memory dump. Why? Because you probably haven't used a lot of it. However, in the field we're in, you're going to be using a lot of it, so kind of get ready, you're going to end up having to memorize a lot of this. So we have 3 different categories here, and 2 of them are kind of tied together. So you have scientific notation, or scientific, I'll just leave it at scientific notation. This should be something familiar to y'all because you have used it before. You might not have used it in a while, but you do have used it before. This is a great way of looking at big numbers and making them small enough to deal with. Right? You have engineering notation, which we'll get into that, and then engineering and metric prefixes kind of go hand in hand, and you'll see why when we get to that. All right. So before we go into it, and guys, feel free to unmute and talk and say whatever you need to say on this, but what do y'all remember of scientific notation? Anybody?
Actually, I don't know what this means. It's like it's not calculation or something, no? Or
So
like how to calculate like the power of speed or something like this.
you're kind of close and kind of not. So does anybody else want to take a stab at it? All right, so who remembers their metric prefixes? Again, we're talking about the King Henry danced merrily drinking chocolate milk. You had to learn that in middle school science, I believe. So scientific
Yeah, but
notation,
I have like
go
yeah.
ahead.
Go ahead, mister.
All right, so
No,
scientific,
I said just.
go ahead.
I'm sorry. Yes, okay. Just this different background of high school. That's why I don't know that one.
That's fine. Okay, so scientific notation. This is a special format of a power of 10 that allows us to look at big numbers in a smaller way. Okay, that is probably the easiest definition I can give you of this at this time. But what does it mean? Well, it means that it's exactly what we've been doing for the past few minutes. Um, it's bringing big numbers down to a smaller value. Now, the thing you want to remember with this, guys, is the fact that with scientific notation, there can only be, but in front of the decimal, so if this is my decimal right here, the number here can only be between 1 and 9. Okay, it can only fall between the numbers 1 and 9. There's only ever that one number in front of the decimal. Now, to clarify that, you also have to have one number in front of the decimal. We'll get to that in a second. So if I've got, so the way they've shown you here is that they start off with 150,000. You simplify that into 1.5 times 10 to the 5 because where's my decimal supposed to be? In every number you've got. On every number that's out there that has ever been created, discovered, what have you. Okay? Where's the decimal supposed to be? Where's the decimal hang out, guys?
Behind the number?
It's at the very end of the number, yes. The decimal point on a whole number is always understood to be right there. We just don't write it because what's the point, right? So when they're moving this decimal, they're counting it up and putting it in your exponent. So if you move it 1, you move it 2, you move it 3. So far, have I got a single number in front of my decimal place that's one numeric value? Answer is no. So I got to keep going. 4. I've now got some numbers in front of that decimal, but there's only supposed to be how many?
At least one?
Not at least. It has to be no more than 1. So I can't have 15. I have to move it forward one more place. So I've now moved my decimal 5 places, 10 to the 5th, and my decimal is falling between my 1 and my 5. So I get 1.5 times 10 to the 5th. Does that make sense? Yes, no, maybe so. I'm getting a lot of crickets today.
It makes sense.
Okay. So then let's look at the other one. This is showing you the value of a negative number. Okay. So again, we're putting this in scientific notation, which means I need a number between 1 and 9 in front of my decimal. And that every time I move that decimal has to be counted. So with the decimal, I don't have to say that it's understood, it's visible. So I move it 1, 2, 3. I still don't have a number in front of that decimal. I move it one more place, and now I do. So now my answer becomes, how many times did I move it? Well, that's 10 to the negative 4 since I moved it behind the decimal. And my number is 2.2 because that's where my numbers ended up stopping. Easy enough?
Yes, ma'am.
Okay.
Can we do it 22 times 10 square 5 minus 5?
No, and that's because you have to follow this rule right here, is that you have to have, the number has to fall between 1 and
1 to
9. In other words, it has
Okay,
to be greater than 0 but less than 10.
great. Thank you. I missed that.
That's fine. So your number has to be greater than 0, less than 10. That is the very premise of scientific notation, is that it falls between those two. All right, so I'm going to let y'all have a little practice with this. And I'll give y'all just a minute to work on it. And then we'll go back in and we'll talk about the answers for it. I'm gonna give y'all just another minute and then we'll start going over answers, guys.
Okay, thank you.
All right, so what did everybody get for 82,000 for your scientific prefix? I'm sorry, your scientific conversion.
8.2 times 10 4.
It is 8.2 times 10 to the fourth. Does everybody agree with that? Okay. About 3,000.
I'll let somebody answer, I guess. I know the answer, but
Yeah, I think everybody's being very quiet today. So yes, it is 3 times 10 to the third. For this guy, so guys, like I said, whenever you're dealing with anything like decimals and they don't already have that comma, put the comma in there. It makes it a lot easier to track yourself. And something like this, where you have to be able to track your numbers very closely and how many times you move it, it gives your brain a visual break stop, so you can sit there and go, oh, here's 3 places, and here's 3 places. So this means that I'm dealing with these numbers. Versus dealing with a decimal sometimes so long that you just sit there and go, huh? So for this one, you should have had 2 times 10 to the -4. For this one, you'd have 6 times 10 to the -1. 2.43 times 10 to the 5th. 7.5 times 10 to the 4th. Once you solve 1 over 500, that's 0.002, which is 2 times 10 to the -3. Here we got another long decimal, so what I'm going to do is go in and put commas every 3 places, just like you would for money in the first part of the decimal, right? putting that in makes a visual break that also makes that number a lot more manageable. Would y'all agree?
Yes, ma'am.
So get used to doing that, guys. It doesn't mean that it changes the value of the number. All it is just a visual place that your brain can go, oh, this is what I'm looking at. Because it's actually been proven that the human brain can only recognize so much before it goes into meltdown mode and you have no idea what you're doing. So in this case, we end up with 2.56 times 10 to the negative 6. Now looking at this number, again, with scientific notation, what do I have to make sure of?
Greater than 9, greater than 1 and less than 9.
The number has to be greater than 1 and less than 9. So I go up to my one number, my last, or I guess you could say first number in this whole number, and that's a 1. So I end up with 1.956 times 10 to the 6th. This is 1.2 times 10 to the 7th. And I'm just rounding out the 4.04.
Oh, okay, okay.
Just because that starts to get a bit much to write when you're trying to do it with a mouse.
That's right.
So the decimal for this guy is 0.0005. So we end up with 5 times 10 to the negative 4. Here we end up with 0.2345662, or 2 times 10 to the negative 7. Now see how I got all those numbers? All right. Any questions on converting to scientific notation, guys? Now's a good time to ask before we move on.
I'm good, thank you.
All right. So let's talk about engineering notation. Now, engineering notation is a very interesting notation, simply because you've probably used some of it, even if you have never really thought about it. I know a lot of people have never even thought of, much less heard of, engineering notation outside of classes like this, but you have used it. So these run in multiples of 3. So if we go back to currency and we're dealing with multiples of 3, think of it like any kind of currency we use. Anytime you get to past 3 value places, so 1, 2, 3. So let's say I've got, I don't know why all of a sudden it's doing that. Anyway, So this is a special form of powers of 10 and moves in multiples of 3. So once you get to every comma in your number, so let's say I've got 2, 5, 7, 4, 6, 0, 0, 0. So this moves by the power of 3. So it moves with your comma. Okay? Does that make sense? So essentially this moves and lives by the comma that we use to separate different delineations of currency. Does that make sense to everybody? We'll get into it here in just a second, some more. So the number can be 1 to 3 digits times 10 raised to a power. So the number runs between 1 and 999 in front of that decimal and moves by the power of 3. So what do I mean? Well, looking at this, the number is 33,000. In scientific, which is what we just did, you move that decimal place till you get only one number in front of that decimal. Do y'all see what I mean? However, in engineering notation, I'm looking to follow this guy. I'm looking to follow the comma. So thus, my decimal point starts here, and I jump it forward 3 places, which is how I end up with 33 times 10 to the third. Do y'all understand where I'm trying to go with this, guys? So you're not chasing smallest numbers you can get, you're chasing the comma, yes. So for scientific notation, when we come to 0.045, for that we ended up moving our decimal place 2 places to get 4.5 10 to the negative 2. However, with engineering notation, you're moving it by places of 3. So that's how you end up with 45 10 to the negative third. That kind of makes sense to everybody?
Yes, ma'am.
Okay. Just trying to make sure I don't lose anybody in the run here.
So what's the rule in engineering calculation? It's from 1 to 999.
Yes.
999.
So the number here can be between 1 and 999 because we're moving by powers of 3. So let's say
Okay. Always we have to move by 3, right?
You have to move by 3s, exactly. You cannot move by anything but the power of 3.
Okay.
So if I have a number that is 276,000, then I'm going to move by first one there. Since I've got at least one whole number in front of that decimal, I would stop there, and that'd be 276 times 10 to the third. Does that make sense?
Yes, ma'am.
All right, and if I ended up behind the decimal, so let's say I've got 0.6. Well, I have to move it by powers of 3, so I'd end up moving it 1, 2, 3, and that's where those understood zeros and decimals start coming in here. So I would end up with 600 times 10 to the negative 3. Does everybody see how I did that? Because what is around every number? So I don't care if it's 0.6 or 6 million. Understood behind and in front of numbers until they're given value are these invisible zeros, right? These zeros have no value until we give them value. Does that make sense to everybody? So that's what allows us to move this decimal so
Yes, ma'am.
easily. So anybody got any questions before we move on? And we'll probably end up working those same problems. This time we're doing them in engineering notation. And I will let y'all work on this for yourselves for just a minute, and then we'll go over it and see how y'all did. All right. I'll give y'all just another minute to work on this, and then we'll go over the answers.
Okay, thank you.
All right, guys, so once again with this, you're going to follow the comma. So the first one ends up being 82 times 10 to the third. Your second one ends
That's
up
right.
as 3 times 10 to the third. Remember, you're just following the comma. So looking at this guy, so we move his place 3 times, so 1, 2, 3. Do I have a number in front of that decimal yet?
Not yet.
Not yet. So I move it, so I have to move it another 3 places. So I move it 1, 2, 3, and I should have ended up with 200 times 10 to the negative 6. Did everybody get that one all right?
Okay, question. We have to move all the time by 3. If we did not find anything by 3, we have to move again by 3.
Yes.
So we don't need to move any till we find one between 1 to 999 and then we stop.
Yes.
Okay.
I think
Because what
I
I
know
did,
what
I
you're
did
talking
just
about.
2.
Huh?
Yeah, I did just 2, and then I did the 2 times 10 to minus 4, and then I stopped. Like I was doing it from 1 to 99.
No, what you have to do is it's got to be by
But
that
we
multiple of 3. The multiple of
okay,
3
okay,
in engineering notation, this is your sacred, this is the part that's kind of sacred for this. I don't know how else to put it.
okay. That means we're looking for 3, 6, 9, 12, and we're going like that.
Yes.
Okay, thank you.
So keep in mind that the power of 3 in engineering notation, guys, has to be the one that is sacred. Okay?
Okay, okay, man. Thank you.
It goes for everybody, okay? Make sure you remember that you're moving in powers of 3. That's 3, 6, 9, 12, 15, 18, so on and so forth. You're moving by that multiple of 3. Okay? So for point 6, again, we got to move by that multiple of 3. 2, 3. This one should have been 600 times 10 to the negative 3. This one would have been 243 times 10 to the third. This one is 75, 10 to the third. If I remember right, this one was 0.002. So this one would have been 2 times 10 to the negative third. This guy, again, you need to go in and put your commas or put some sort of visual break so you're able to break those numbers apart in those groups of 3. Okay? So in this case, we should have ended up with 2.56 times 10 to the negative 6. Does everybody see what I did?
Yes, ma'am.
Okay. So the next one, we should have gotten 1.956 times 10 to the 6. As long as you have, so the trick on this one was to not stop here. Why? Because I have more than 3 numbers in front of that comma. I have 4. So you want to go to the second comma, and that's where your decimal point will go. Does that make sense to everybody?
Yes, ma'am.
Okay. So then this would be 12.04 times 10 to the 6th. This decimal equivalent is 0.0005, which would have ended up giving you 500 times 10 to the negative 6. And then this last one, you would have ended up with 200 times 10 to the 9th. Sorry, to the negative 9th. So does everybody see how I did that?
Yes, ma'am.
Any questions from anybody? All right, so again, here's your answers. And guys, I'm serious about doing that visual break. I can't tell you how many times I've had people come to me with problems like these and go, I don't understand what's going on with this. Well, if you do this visual break, it's much easier on your mind and easier on you as the person having to do the mathematics on this to have that visual separation. So especially on big numbers like these, being able to just go 1, 2, 3, comma, 1, 2, 3, comma, suddenly breaks a number that is very long and very monotonous into one that is a little bit more easily understood by your brain. So the term floating point means that there is no fixed number of digits before and after the decimal point. The good thing about floating points is that it does allow us to have a bigger ability to range our numbers. So we don't have everything confined to the decimal point. It's a lot less precise. So what do I mean by that? Well, let's take somebody like some of the billionaires. Do you really think they deal with nickels and dimes as far as their bank accounts go? Or do they look for the, yes, you have $1 billion? You know what I mean?
Yes, ma'am.
So they tend to use a floating decimal point just like this. Why? Because it allows them to have a little bit more freedom. As far as not having like 1,000,001 numbers across a bank account. They're not going to deal with nickels and dimes. They don't care. They want to know, am I still a billionaire? Okay. So that's what the term floating point number is, because that's how we deal with this. So the next thing we're going to talk about is the metric system. Who remembers anything at all about the metric system? It's base 10. That's part of it. Yep. What else?
It's easy. It's not like the other ones.
It's what now?
I said it's easy.
It's a lot easier to deal with than what the American standard system is. I'll go ahead and tell y'all, they've been trying their hardest to try and get us to switch over to metric for years. The only reason we haven't switched over to this is because a lot of people have drugged their feet about it, and everybody just said, never mind, we will let everything go. So that's why we have not converted yet. It would probably be easier for us if we did, but too many people have drugged their feet about it, and basically everybody says, okay, we'll let you alone. It doesn't matter that much. Only it's a lot easier. So just to kind of give you a comparison, looking at the US standards, these used to be the standards worldwide, but now it's, I believe, only 3 countries. The other name for it is called Imperial, and there's only 3 countries. There's us, there is Liberia in Africa, and Myanmar in right beside India. 3 countries, guys.
Wow, those two countries in the middle of like everybody using metric, they using US gallons and this. Yeah.
Yep. We're the last big holdout. England still has a bit of a mix of it, but just about everybody's gone to metric, and there's a good reason why. So when it comes to weights and measures, so let's kind of talk about what the difference is between something like, think about it this way. How many inches are in a foot? 12. How many feet in a yard? 3. Goes into acres. Well, what's an acre? What is a mile? None of these have consistent anything to them. They say that the foot was based off somebody's foot. And like somebody says a city block. Okay, so what's a block versus a city block? You have surveying lengths, leagues, furlongs, chains, statute miles, rods. It just kind of gets ridiculous and funny when you start really looking at these. If you ever really start looking these up, it just sits there and goes, wow. There is no real consistency about any of this, right? Because if you go for something like drops versus drams versus teaspoons, dessert spoons, tablespoons, cups, pints, quarts, gallons, barrels, oils barrels, and hogsheads. And yes, there is such a thing as a hogshead as a measurement. I don't know who came up with it. It's roughly 63 to 64 gallons of something along the lines of beer. I don't know what that's got based on, but for heaven's sake, that's a little strange. So, and then dry volume, of course, you've got pints, quarts, gallons, pecks, bushels, barrels. I mean, it goes on and on. Does anybody even know what a troy weight is or what it's used for? For those of you that don't know,
I don't have no idea.
it's based on not just so much gold measurement, but precious metal measurement. If you're looking to buy something like silver, gold, copper, this is part of the way you can buy them, and that is in what's called troy weights. And that is simply how they measure out how much of it that you've got. So if I was to buy a bunch of silver wire to make jewelry, I can either buy it in troy ounces, or I can buy it in feet or yards, whatever I need to buy it in. But troy ounces is one of the things that you can buy this kind of stuff in. Same for gold, same for platinum. Troy weights is one of the ways that you buy these kind of things. It's for precious metals. So then we get to something like the metric system. There is one thing for length, one thing for volume, one thing for solid weight. Just one, and everything is base 10. Okay, so we have what are called metric prefixes, which are symbols and terms used to represent the most common powers of 10. So each letter or symbol replaces an engineering value. So we have, and you've probably used some of these. I know everybody knows what milli is because, you know, it's one of those that we have used before. You know, micro. Nothing else, you've used it in the word microscope. Giga. Well, what do you buy a flash drive in? You buy it in a gigabyte, right? Everybody should know the word kilo, right? Nothing else. You have kilometers versus, or you can say I bought a kilo of flour. Different things like that. So this is the metric table. So we have pico, nano, micro, milli, kilo, mega, giga, tera. And I'll tell you right now, right here, between these two, there is nothing that represents numbers 1 through 999. This starts at 1,000. This starts at 1,000ths. So this starts behind the decimal. This is where your decimal point is right here. This guy starts after 1 to 999. Okay? There is no metric prefix for those that we will be using. Does that make sense to everybody? This is where the fun part comes in. So we've heard of some of these. I know a lot of you probably don't know what tera is or where it might be used, but how many of you have bought a computer in recent times? If you go to Best Buy, you have the higher end computers and the more expensive computers. You can buy a terabyte hard drive. Terabyte, petabyte, zettabyte, yes, those are all memory terms as far as how much memory something is able to hold. It's all about how much memory does something hold. Okay, so the bigger the memory, the more it'll allow you to have and the more you can put on it. It also can raise the speed of the computer. Giga and mega, and kilo, we've used a lot. If nothing else, if you want to go back to memory, I believe the old floppy disk had about a couple kilobytes of memory, maybe. When the memory cards, the flash drives first came out, they had roughly a megabyte's worth of memory. Now we talk about gigabytes of memory. And terabytes of memory. So all of this is kind of evolved. Then you get to things like milli, micro, nano, and pico. And these are all smaller things. So micro, think of something being put under the microscope. You're looking at something very, very small, something the size of single-celled organisms. Okay? You've probably heard the term nano a few times. Things like nanobots and things like that they try and create. So you have heard some of these, even if you've not put them in practice. So to give you a bit of practice now, I'm going to go ahead and let y'all turn loose on this. We've already done this in in engineering notation, so now you need to just put your metric prefixes with them. I'll let y'all take a minute to do so. All right, so at 82,000, what should be my metric prefix here? It should be 82 kilo or 82K. And the same should kind of go for this guy too. That should be 3K. So what about this guy?
Uh, 0.2 kilo.
Nope. So if we go back to this again, we've moved it 3 places. That would have been milli, but I don't have a number in front of that decimal yet. So I've got to move it another 3 places. This should have given you 200 micro. And the sign for micro, guys, kind of looks like a U or a skinny topped M. Okay? It looks like either a U or a skinny topped M. And that's the symbol for micro. So micro, and again, you can kind of lengthen one side or the other. It just kind of depends on what you want to do. So what about numbers? What about this guy right here, the 0.06? I'm sorry, 0.6. Getting ahead of myself here. Anybody want to take a guess? And the answer for that one should be 600 milli. That's represented by a lowercase m, guys. So this one, just like the one above it, you end up with 243 kilo. You end up with 75 kilo here. So this one, the decimal format is 0.002, which would have given you 2 milli. Breaking this up, I move my decimal point 3 places, which would be milli. But I don't have a number in front of it. I move it another 3 places, so it should be 2.56 micro. Everybody following so far?
Yes, ma'am.
Okay. This guy is 1.956. So here's kilo. Here's mega. So you end up with mega, which is an uppercase M, which I'm having a hard time doing right now. So it's 1.956 mega. In which case, we'll call this one 12 mega. It's an uppercase M. This one is 0.0005. So my comma starts here. Now I would have another comma out here. 2 zeros behind the 5. End up with 500 micro. And then this guy is 0.8. Sorry, I'm trying to write this down and it's not. I had 2 extra zeros there. So this is 0.00000000002, which when you start doing your calculations, have to add another comma out here, and you end up with 200 nano. Okay, you end up with 200 nano. Did everybody see what I did and how I did it? Okay. Does anybody have any questions on what I was doing here? All right. So y'all might want to take a picture or a screenshot of this because this is one of the best metric conversion tables I know of, and I will try and provide y'all with one soon. But that's going to make sure that y'all need to be in class. which, by the way, starting next week, we will be doing labs and stuff in classroom and be able to be on campus. So do be planning for that, guys. So this kind of provides you a way of looking at it all. So if nothing else, you need to remember where your decimal point permanently is supposed to live. And that is right here. This is where your decimal point permanently lives on a normal number, right?
Yes, ma'am.
So that being said, this is why I say, when in doubt, write it out. Because once you figure out where that decimal place is in relation to where your numbers are, it's a lot easier to figure out what prefix you're playing in. All right? All right, so just so y'all have a little bit of time to work with it, by the way, anybody need a last minute check on this, or everybody good?
I'm good.
Okay. So let me pull over this. So this is, again, our Blackboard site. If you go under assignments, activities, and course content, which this always takes me a minute to load, you should be working on your math quizzes. Again, I've left those open so y'all can take them however many times you want. So you can make whatever grade you want. So the module we're currently on is Module 4. And if you go under Module 4, this is where I've got some practice things for y'all to play with, including Lab 1. Now, Lab 1, I thought I got rid of a bunch of this, but apparently not. I'll do it later. So looking at Lab 1, I'm going to go ahead and pull it up for y'all. If this will do what I'm asking it to do. What the heck? There it is. Okay, so here's Lab 1, and this is something that you can kind of consider homework, so you might want to start working on it. And I'll have a way for y'all to turn it in soon. I keep trying to. I won't even get into that. So what you have are several tables. The first table, you're dealing with positive sides of the power of 10. What you would do is what you're going to do with this is you need to put everything into scientific notation, which, what did we say scientific was? Scientific means you only have one number in front of the decimal, and that number is between 1 and 9. And you have it times the power of however many times you move that decimal. Then you're going to give me the engineering portion of this, where you're going to say, so for the first one, it'd be 12 times 10 to the third. Lastly, you'll give me your metric prefix. If you don't remember your metric prefixes for a bit, that's fine. I've got a table up here. So for this one, it would be 10 to the third. Look up to this one, and you see that's kilo. So I'm looking for is either 12 kilo or just the word kilo, a K, what have you. You would do that for all these problems. Okay. Table 2 is where you're dealing with the negative powers. okay? Same thing as what you did up there, only you're dealing behind the decimal. Then thirdly, here's another table. This one's got a mix of both. Now table 4, let's kind of talk about this one. Table 4, anytime you see the words multiplied by, that means you're going to add your exponents. Where you see divided by is going to mean you subtract your exponents. So the first one for divided, we have -6 or micro minus -9. Now let me ask you this, can you subtract a negative? Can you subtract a negative? The answer should be the answer to that one is no. You cannot subtract a negative, you turn it into a positive. So what this would be -6 plus 9. So you would end up with kilo as the metric unit result. For milli multiplied by milli, so that's -3 plus -3, which would be a -6. Y'all see where I'm going with this? Those of you playing at home, y'all kind of see where I'm going with this? So I'll leave that for y'all to do, and we'll talk about it whenever we come back on Monday. And then these questions are a couple more, and we'll go over a little bit of these a little more in depth as we go. But for right now, I want y'all to use these tables as practice so you can start getting this down. Part of what you need to make sure you do for memorization for this class is you need to have this right here. You need to have these memorized. So if you see something like a -3, well, that's milli. -6, micro. +9, that's giga. I want y'all to go ahead and start getting that memorized, okay? And that'll be your main point of homework for this weekend. Sound good?
Yes, ma'am.
All right, then